All right. Well, congratulations on surviving until the last day. Congratulations to me also, the same. So as I kept promising during the entire course, eventually we are going to go to 2 dimensions, which is today. And the reason why 2 dimensions is nice is that there are actual exact solutions, which are non-trivial, of the setup that I was presenting in the previous lectures. So everything that I said so far about conformal field theory in general dimension is also true in 2 dimensions, but there is some additional structure and additional symmetries in 2 dimensions which make the problem a little bit more solvable. In higher dimensions, there are of course many CFTs that we believe exist, but essentially the only exactly solved CFT in higher dimensions is the free scalar, or any free theory. Whereas in 2 dimensions, there are various other solvable examples, in particular the minimal models that we are going to look at today. So why is 2 dimensions slightly different, or what is the extra enrichment that happens in 2 dimensions? Well, it's because the conformal killing equation has more solutions than in higher dimensions. So let's remember the conformal killing equation. So we have some vector field VA, which now in 2 dimensions, A can take only 2 values. No, everything is 2-dimensional. And the geometric transformation needs to satisfy the conformal killing equation, which is this one. So now we are working in flat space, so in R2. DAVB, DBVA. Well, in general dimensions, we saw it was like 2 over D, DCVC. But in 2 dimensions, this is just 1. So this amounts to, you can check for yourself, this amounts to 2 equations. Essentially D1 plus I, so partial 1 plus I partial 2, V1I, V2. So it's kind of useful to organize everything into holomorphic and anti-holomorphic coordinates. Okay, so this is equivalent. You can check, you can go from here to here, which means that now the space of solutions that in higher dimensions was finite dimensional, now it actually becomes infinite dimensional, because V1 plus IV2 can be any, so this is like the anti-holomorphic derivative, can be any holomorphic vector field, and Vi minus IV2 can be any anti-holomorphic vector field. So we can, so V1 plus IV2 should be some arbitrary holomorphic function of Z. And Vi minus IV2 is some anti-holomorphic function of Z, which if you want a vector field which is real in Euclidean space, F tilde should be the complex conjugate of F. But in general, if you work like in the complexified Lie algebra, it doesn't have to be. Okay, and the point is that there are of course infinitely many holomorphic functions, because we can we can choose a basis where f of z is just arbitrary power of z. And in fact, okay, let's introduce some vector fields. This is supposed to be calligraphic small lowercase l. So let's introduce these vector fields where Ln is Zn, z to the n plus 1, and so partial z. I'm going to use the notation that partial z is just partial, and okay, sorry, z. I should say z is of course x1 plus I x2. So z bar is x1 minus I x2. Okay, so let's introduce the notation that Ln is this vector field, and Ln tilde is a different vector field, which is this complex conjugate of it. Okay. This vector field is singular at the origin when n is less than -1. But this doesn't really bother us because we are going to go to the cylinder, and as soon as we go to the cylinder, the cylinder doesn't contain the origin and the infinity. So on the cylinder, both of these vector fields are smooth and have no singularities. Okay, but so before we go to the cylinder, let's compute the Lie brackets or the commutation relations of these vector fields. So if we remember that if we act on functions, which is what we want to do, we need to add an extra minus sign. So somehow the commutator of the action is minus the Lie bracket, right? There is this funny minus sign which you should try to think about carefully if you're confused by it. I mean, I was confused about it for a long time, but so it's the commutator is not very hard to work out. Well, we should put these extra minus signs, so we would have z to the n plus 1 partial, z to the n plus 1 partial. So this minus cancels this minus, and when this one hits over here, the other one hits over there. So ultimately, you end up with n minus m z to the n plus 1 partial, which is nothing else than m minus n L m plus n. Okay. So the final result for the commutation relations is that the commutator of Lm Ln is m minus n L m plus n. The same thing is true for the Lm tildes. And finally, the LMs and the LM tildes commute with each other. So they're completely decoupled at the moment. Okay, so these are the computation relations of the geometric transformations. So far we are not really doing physics. There are no operators, no states. So far this is just geometry. Yes. So yeah, this is the thing that we were discussing a few lectures ago, that a vector field represents an infinitesimal motion, right? And if you act on functions, you need to shift the function by the negative vector field. So that's the minus sign, right? Because if you're moving a function to the right, you're hitting it with minus derivative with respect to x. I guess I could have introduced different notation for the vector field and a different notation for the action on functions, but there would be so many different L's that we would get lost in it. Okay, and this is called the VII algebra. Usually one copy of it is called the VII algebra, and now we have two copies of the VII algebra, the Ln and tildes. And so now we can go to the cylinder, and these geometric transformations are going to become some geometric transformations on the cylinder, and therefore they're going to become the symmetries of our conformal field theory. So we expect that these L's, Ln's, can be promoted to quantum operators. Operators acting on the Hilbert space of the theory on the circle. So now the circle, so the cylinder is quite simple. It's just S1, S1 times R. So now this picture becomes completely faithful. And V is just the Hilbert space of our two-dimensional conformal field theory on S1. And it should be a representation of quantum operators, L and L tilde, which arise from quantizing these, which arise from these symmetries. But there's an important caveat. Okay, before we go to the caveat, let me relate what we've said so far to what we did before. So if you, from the previous discussion in previous lectures, we would say that two-dimensional conformal field theory has 6 symmetries. The 6 symmetries would be P1, P2, then D, M12, and K1, K2. Okay, so there's only one rotation in 2 dimensions, and these are special cases of these quantum operators where P1 and P2 are linear combinations of L minus 1 and L minus 1 tilde. These are L0 and L0 tilde, and this one is L1 plus or minus L1 tilde, right? So it's all you have to do to understand it is to look at these vector fields. For example, when n is minus 1, when n is minus 1, you just have the holomorphic derivative, anti-holomorphic derivative. So these are translations. So these correspond to the P1, P2. Then L0 for n equals 0, you have z dz, z bar dz bar. So their sum is just the dilatation, and their difference is a rotation. And finally, for K1, K2, for the n equal to 1, you get something quadratic in z and z bar, which is exactly what we saw for the special conformal transformations. Yeah, okay, so at this level, there's a perfect match, but in 2 dimensions, we also have these additional generators where absolute value of n is greater than or equal to 2. And here comes a kind of a subtle point, which we didn't have to deal with in higher dimensions, which is that in quantum theory, the representation of physical symmetries on a Hilbert space does not have to be a representation, a genuine representation, but it can be a projective representation. Right, so in quantum theory, suppose we have some physical symmetries which are represented by a group. So we have some group elements. We have a group G, and its elements satisfy some multiplication law. Then on a Hilbert space, Wigner told us that these would be represented by unitary or anti-unitary transformations, but these transformations don't have to satisfy the same group law. They do have to satisfy the same group law, but only up to a phase. I mean, this is because physical states in quantum theory do not correspond to vectors, but rather to arrays of vectors. Right? So if you multiply a state by any complex number, you're going to get the same state, which is why we are allowed in quantum theory to have this extra factor, making the representation a projective representation. So this is how it looks like. This is how this modification looks like at the level of the group, at the level of Lie algebra. So let's imagine that now. Let's imagine that x1 and x2 are in the Lie algebra. Then at the level of Lie algebra, this failure of the homomorphism property would look like this, right? If we take the commutator of the representatives, we should get the representative of the Lie bracket So this is kind of the abstract Lie bracket, and this is the genuine commutator of matrices. But there could be an additional term, which is just a C number. This is just a number, right? This number is kind of the differential of that exponential. Okay. And of course, this is already familiar from higher dimensions, not from it's familiar from quantum field theory. Is this the reason why we can have fermions? Because fermions correspond to projective representations of the Lorentz group. Because if you do a 2 pi rotation, you don't come back to itself, but only to itself up to -1. In two-dimensional conformal field theory, the enrichment of the situation is more dramatic because there could be a genuinely new term in the commutator. So these quantum operators need to satisfy the same algebra as their geometric predecessors, but only up to an additional term, AMN, which should be some complex number. But what can this be? It cannot be arbitrary. It's because it still has to be consistent with properties of commutators, right? So the empirical there's an important property of the commutator that LA, LB, LC, well, plus this is called a Jacobi identity. LB, LC, LA, LC, LA, LB. This is equal to 0. This is not an axiom. This is just a theorem of commutators. Okay, if you expand everything, you get 0. And this gives you a constraint on AMN. In this particular case, what you find, I mean, it's a simple exercise. You find A minus B, so that's from here. Then LA plus B, so we get A plus B, C plus B minus C, A, B plus C, A, plus C minus A, C plus A, B, equal to 0. But you can also redefine these L's up to a constant. So imagine you shift LA to LA plus some arbitrary function of A, which is a C number. Then this allows you to modify A of A to A of A plus A minus B of A plus B. Okay, so the most general term here. Okay, sorry, this is called a central term. It's central because it's just a number, so it commutes with all of the generators. And the most general one, which is consistent with the algebra, is one which satisfies this property. But we are allowed to change. We are going to switch the gauge in this way for any f. So f is a function from Z to C. And A is a function from Z times Z to C. Okay. And yeah. Sorry. Okay. Yeah. And okay, this kind of problem is a special case of Lie algebra or Lie group cohomology. This is, I think, the second cohomology, and this is kind of a constraint that something is closed, but you only care about it up to some exact terms. And it turns out that in this case, the cohomology is one-dimensional. Yes. Well, you can always redefine the generators up to some number. That's like, yeah, that's kind of like, yeah, you're adding a phase to the group element, or you're yeah.
So it must be the same for all the elements of the algebras.
Well, this f could depend on A. You could just yeah, you could redefine your generators in this way. You see, if you redefine like that, it's not going to modify the first term, because this f commutes with everything, but it's going to modify the last term. Yeah. So here the solution space is one-dimensional, and it looks as follows. It's a very famous algebra called Virasoro algebra. So the non-central part stays the same, and then the central part looks as follows: C over 12 times m minus 1, m plus 1, and the Kronecker delta of m n minus n. And so C is a, for now, arbitrary complex number. So that this is the one dimension of the solution space. So basically, I can use this f to make the central term vanish unless m is equal to minus n, and then it's uniquely constrained to look like that. Something that you can notice is that it disappears. So this a mn is 0 on the global part. So if as long as m and n are minus 1, 0, and plus 1, this term is not there, so we get this. We don't get anything new. I mean, we get an algebra which agrees with the global algebra of the p's, d's, and k's. But for m outside of this range, we get a genuinely deformed centrally extended algebra. Okay, so this is called the Virasoro algebra. And we get the same kind of thing for the L tildes. Where in principle we could have a different C, some different value. I mean, so far from what I've said, it doesn't follow that they have to be the same. Okay, so this is maybe the most important point of this lecture, is that the Hilbert space of conformal field theory on S1 is a representation of two copies of the Virasoro algebra. Okay, so the V on S of the theory on S1 is a representation of Virasoro algebra, and we usually denote the Virasoro algebra by the central charge. Okay, sorry, I should say, yeah, the C, this pair of C and C tilde are the central charges. I mean, usually they are the same, so it's just called a central charge, but I'm not assuming it, so let's call it central charges. And this Hilbert space is a representation of, well, I guess of direct sum, because we are talking about a Lie algebra. So of the direct sum of and usually sometimes people put the tilde here, but it just means that this is the one, this is the holomorphic one, this is the anti-holomorphic one. Okay. Mm-hmm. You could try to do it, but you will find that this cohomology problem has no solution. The space is zero dimensional. Mm-hmm. Yeah.
The version of central charge in string theory appears to be just normal order constant. Whereas over here, like it's just consequence of having projective representations. So just like what's the
Good. I mean, I guess a normal ordering constant is something that's a bit special to free theories. So, but there's a way to reformulate what central charge is in general conformal field theories by talking about a stress energy tensor. So in these lectures, I've been kind of avoiding talking about a stress energy tensor, but its basic central charge, from that point of view, is the failure. It measures the failure of the stress energy tensor to be a primary under the entire Virasoro group. It also measures the Weil anomaly. So, I mean, there are various ways in which the central charge appears. So maybe I can mention them later, but I need to get to minimal models today. So, but you're right. There is central charge appears in many different ways in the study CFT. Okay. Yeah, are there any other questions about this so far? Okay, so now we have V of S1 as a representation. And we need to talk about unitarity. So remember that unitarity manifests in the following way. It says that if you have that any real vector field on the Lorentzian cylinder should become a anti-Hermitian operator. And so we can just ask which of the small L's correspond to real vector fields on Lorentzian cylinder. Okay, let me just remind you, how do we get a Lorentzian cylinder? Well, we have x1 plus ix2 in the plane. We can write this as e to the tau, now e to the I theta, because now this is the S1, right? So theta parameterizes the S1. Oh, theta is between 0 and 2 pi and parameterizes the S1. Tau is the Euclidean time. And the Lorentzian cylinder is the pair of points t theta where tau is it. So we only continue from the Euclidean tau to Lorentzian tau. So this is the Lorentzian cylinder. And we want to find linear combinations of little L's, which are real vector fields on this space. And this is the answer. Okay, not so hard to check, so I'm not going to do it explicitly. I'm just going to give you the answer. It's the difference is the difference between ln and L minus n, and the sum with an I, as well as the corresponding thing with tildes. Okay, so when we go to the quantum operators acting on the Hilbert space, each of these have to be represented by an anti-Hermitian matrix operator, which can be summarized by So as, you know, as an exercise, you can just find what this thing looks like as a vector field on tau and theta. You're going to find something like this. This looks like I think sine and theta, I think, and dt minus d theta, basically. This thing is a cos. And with the hats, so with the tildes, instead of having a dt minus d theta, you're going to get dt plus d theta here. But they're all real vector fields. So what this means, unitarity, is the statement that there is a positive definite inner product on V of S1 such that ln dagger is L minus n, and ln tilde dagger is L tilde minus n. Okay, well, by the way, yeah, I should have written also that ln commutes with ln tilde, but somebody already asked about it. I just didn't write it. Okay, so these are the unitarity constraints. Okay, now okay, so now we want to understand the Hilbert space on S1 as a unitary representation of this algebra. Now remember that dilatation is L0 plus L0 tilde. That's because the x1 d1 plus x2 d2 is the same thing as z dz plus z bar dz bar. Okay, so this is L0 and this is L0 tilde, and this is what I call little d. And this is our Hamiltonian. And in a reasonable quantum theory, the spectrum should be bounded from below, just like in higher dimensions. So the spectrum of D is bounded from below. So we should ask ourselves, how do if we act on a various states with these generators, how are they going to modify the energy? Right, so notice that if I take the commutator of L0 with Ln, well, from over here, I get minus n Ln. So both Ln and Ln tilde lower the energy. So lower the energy by n. Okay. So eventually I have to reach a state which is annihilated by all ln's and ln tildes with positive n. Okay, maybe let's leave this one. if we keep applying the ln's and L and tildes with n positive, then eventually they're going to annihilate our state. So this leads to the notion of Virasoro primary state or operator. We have a state operator correspondence, so it's the same thing. Is a state psi which is annihilated by all the ln's and ln tildes with positive n. And this is a generalization of what we called conformal primary before, because in general dimension, conformal primary was the one annihilated just by L1 and L1 tilde, so K1 and K2. And this in 2 dimensions is just called global primary or global conformal primary. Is the one that just annihilated by L1 and then L1 tilde. So every Virasoro primary is a global conformal primary, but not every global conformal primary is a Virasoro primary, which partially explains my answer to your question from yesterday. There have to be infinitely many global conformal primaries, but there can be finitely many Virasoro primaries. Thanks. All right. So what are the representations? Well, any irreducible representation whose energy is bounded from below can be obtained by starting with a Virasoro primary and acting with all of the raising operators. So just like you saw over here, just like the ln's with positive n lower the energy, all of the ln's with negative n raise the energy by amount n. And we can apply them as many times as we want, and we are probably going to keep generating new and new states. So we have the notion of these lowest weight representations. Which notice that the 2 Virasoros, which are usually called left-moving and right-moving, or holomorphic and anti-holomorphic, the Virasoro and Virasoro tilde, they don't talk to each other, so we can just talk about them completely separately. So the lowest weight representations of the Virasoro times Virasoro of the 2 Virasoros, they can be written as tensor product. So now it's genuine tensor product of the where this is a lowest weight representation of the left Virasoro, this is lowest weight representation of the right Virasoro, such that so what is RHC is the linear span of the lowest weight vector, which let's call it H and C, and then I can keep acting on it with all of the raising operators. So at level 1, there is 1. At level 2, there are 2 of them. L minus 2 and L minus 1 squared, HC, and so on. And what is H? Well, H is the eigenvalue under L0. So when I active, H is like the left moving energy. Okay, so the representation is completely specified by what the Virasoro primary. So this is the Virasoro primary. The representation is completely specified by the central charge and how L0 acts on the Virasoro primary, which has to be like a constant. And then the entire representation is generated by acting with all the raising operators on the primary. Mm-hmm. This tensor product? No. It's so this representation is irreducible. If you this is an irreducible representation of Virasoro plus Virasoro. So here it's a direct sum, but here it's a yeah. If you had a direct, I mean, you already understand, but just in case somebody else didn't understand, is if you had a direct sum, then this would be like this is a trivial representation of the right moving Virasoro, and this would be a trivial representation of left moving Virasoro, but they would be separately irreducible. But their tensor product is not, sorry, the tensor product is irreducible as one thing, as one representation of Virasoro plus Virasoro. Yes?
They verified the lowest state to be Virasoro primary. This means that acting with the creation operators, we can obtain a global primary.
Mm-hmm. So this HC, okay, let me use the shorthand notation H tilde. Okay, a few things. From now on, let's assume that C is equal to C tilde. This is not required if you want to define your theory in flat space, but if you want to define on curved manifolds, it's necessary. Because, so if you want to read more about it, then C minus C tilde is a gravitational anomaly. So if you have a theory that doesn't have C equal to C tilde, then that theory cannot be consistently coupled to gravity in a similar way as the free Weyl fermion in 4 dimensions cannot be coupled to the U1 gauge field. So it's an example of a 't Hooft anomaly now for gauging diffeomorphisms. So let's assume that C is equal to C tilde, and I'm going to denote this representation. Well, I'm going to denote the lowest weight vector of this representation as H tilde C. Okay. So this vector is a Virasoro primary for both this Virasoro and this Virasoro. And it's also a global primary. So I guess I'm finally starting to answer your question. Right, so it's a global primary, but this big representation will contain other global primaries besides this one at some higher levels. We'll see some examples of it soon. Okay. So before the break, let me say something about operators. Okay, so we said that L0 plus L0 tilde is the dilatation, then L0 minus L0 tilde I. Okay, so this is Hermitian, so this is enter. So this is M12. Okay, so this one measures the scaling dimension, this one measures the spin. And so, you know, when M12 can be diagonalized in 2 dimensions, and it's anti-Hermitian, so it's like I times the spin, where spin is spin is an integer. So that means that the operator, which corresponds to the state, maybe we can denote OH H tilde, has scaling dimension delta, which is H plus H tilde, and spin, which is H minus H tilde. Okay, that just follows from over here. So in particular, the physically meaningful representations are those for which this is an integer. In a bosonic theory, in a fermionic theory, this could also be a half integer, but for us, it's always going to be an integer. Okay, so we have an extra constraint that that H minus H tilde has to be an integer. And with this preparation, everything that we said about global conformal primaries in general dimensions in the previous lectures is also true for Virasoro conformal primaries in 2 dimensions, because Virasoro primaries are also global primaries. So in particular, the formulas for the 2 and 3-point functions that we derived in general dimension are also true for these ones in 2 dimensions. So if we have two, okay, let's say, if we have 2 Virasoro primaries, OI and OJ, in 2D, so O corresponds to the state, and then their 2-point function has to take the following form. It's Z. So first of all, it's diagonal, just like in higher dimensions, just like in general dimensions, and then we have Z12 to the power 2H I, and Z12 bar to the power 2H I tilde. Okay. So in fact, this is slightly more general than what I showed you. I showed you how the 2-point function looks like for scalars. So the scalars, if you just want to think about scalars, so scalars have Hi equal to H I tilde, right? Because J is equal to 0. So for scalars, from here, you would just get delta I to the Z12, now absolute value, to the 2 delta I. Okay, so this formula generalizes the formula that I showed you in general dimension to the case with spin. There's also a pretty nice closed formula for the 2-point function of spinning operators in general dimensions, but I didn't show it to you. I mean, it's a little too complicated to write on a blackboard. Okay, so this is the 2-point function of Virasoro primaries. And the 3-point function is an equally simple generalization of the formula. Well, generally, I mean, it's a generalization because now it's going to be true for any spin, but also it's a specialization because we're just taking the Hardy formula and restricting it to 2D. So the 3-point function of Virasoro, or even global conformal primaries, it looks like that. So there is some overall number, Cijk, and then we just have a holomorphic factorization into, let me first write it. Okay, I can already see I'm writing too big to fit. you can imagine what it looks like probably. So it's 1, 3, I, K, J, and 2, 3, J, K, I. Okay, so this is now a completely general formula for the three-point function of any three global primaries, in particular Virasoro primaries, which depends on both the deltas and the spins of the three primaries. And you can derive it in the same way that we derive the higher dimensional formula. It's the most general. It's the most general formula which is compatible with the action of L0, L1, and L minus 1. Okay, and we'll continue after the break. All right. Okay, so we are still in 2 dimensions. We have 2 copies of the Virasoro algebra. We have the lowest weight representations whose bottom vector, lowest weight vector, is labeled by h and h bar. So far could be complex numbers whose sum is the scaling dimension. Their difference is the integer spin. And using what we have learned in higher dimensions, we know that the 2-point functions of any global conformal primaries look like that, and the 3-point functions of any global conformal primaries have to look like that. So this just follows from applying L0, L1, and L minus 1. So I mean, I'm not going to show it to you, but no. So, just a comment, an important comment, which I probably should have made a bit earlier. You can if you know the primary at the origin, a global primary at the origin, you can get the primary at any point by applying the same kind of operator as we saw in higher dimensions. Okay, so if you use this, then the L plus or minus 1, L0 become differential operators acting on the OZ. So you can try to work these differential operators out. In fact, also the L ends and L and tildes for n positive, because these ones are going to annihilate this guy. So these also become some differential operators, but that's just a side comment. And then these 2 and 3-point functions satisfy the word identities arising from these generators. Okay, but now we should think more carefully about unitarity of the representations, because I was a little bit sketchy about it, right? And if you let's just focus on one Virasoro algebra, the left-moving Virasoro algebra. So we are looking at this this representation, which just think of it for now as a vector space with this infinite basis, and using the hermiticity properties of Ln's, we can compute the norms. So if we are assuming that we have this inner product, which is with respect to which the Lorentzian cylinder symmetry is unitary, and then we can use the commutators to compute inner products between these various vectors. And we need to make sure that these inner products are always positive. So it can happen that if we don't choose H and C carefully, it's not going to be positive. So we saw an example of this in higher dimensions, where, for example, if we had a scalar primary operator, then its representation didn't carry a positive inner product unless delta was 0 or greater than the free field dimension. And the same thing can happen here, but here it's a much more interesting problem as a function of central charge and H. Okay, unitarity. So let's just focus on the left-moving representation. So HRHC, and let's ask, when is the inner product here positive? Well, we can normalize it. So we can normalize it to be so that the primary has norm 1. Now we can start computing the matrix of inner product. So let's compute the norm of the level 1 descendant. So we use hermiticity. L minus 1 conjugate is L1. HC. Here we know that L minus 1. Here we know that L1 annihilates the lowest weight. So we can replace it with the commutator. Now use Verso algebra. So the commutator is 2L0. So this is just 2H, right? So we learn that H better be non-negative, otherwise there is a negative norm state. So this is our first example of a unitarity bound, and notice that it agrees exactly with the unitarity bound that I quoted in higher dimensions. So what was the unitarity bound in higher dimensions? For symmetric traceless operator, it was delta greater than j plus d minus 2. So in 2 dimensions, this is just j. So in other words, delta is greater than or equal to j, which is the same thing as h being non-negative. So yeah, 2D is indeed just a special case of higher d. But this is just at level 1, and we should keep going to higher levels. So at level 2, we have these two states. So at level 2, we have states L minus 2 HC and L minus 1 squared HC. So now we have a 2 by 2 matrix of inner products, which better be non-negative definite. And then you're going to find some constraints on H and C. This is actually a very nice exercise that you should try to do. Compute the matrix of inner products and find when it's okay, maybe I'll draw it. Okay, I'll draw it over there. Okay, I should have said two more obvious things first. So firstly, unitarity implies two simple facts. Namely that C is real. That just follows, take the Verso algebra and Hermitian conjugate it and compare. You'll see that it can only be consistent if C is real. And secondly, H needs to be also real. This is just a consequence of the fact that L0 is Hermitian. So, okay, so C is real and H is real. From level 1, we know that H is non-negative. So let's draw. Let's draw the H and C plane. Okay, it turns out that C equal 1 is very special. And C equal 0 is also very special. Okay, so what happens? We should ask for which H and C is the matrix of inner products non-negative. And well, something that you can exclude relatively easily is the C negative. Actually, is that obvious? Okay, I don't even. Oh, sorry. Yeah, this is by looking. Okay, I know how to do it for h equals 0, but I don't actually know how to do it for general h. For h equals 0, you can just look at L minus 2 dagger. But it's a true fact. So this is disallowed. If your C is non-positive, then the representation is not unitary. Now, it turns out that if C is greater than 1, then it's always okay. So is there green? Okay, so this region is always good. Okay, now of course we already said that H negative is not good. Can you see those colors? Like, is this obvious that it's red and then this is green? No. Okay. Well. Okay. Well, I guess it's. You just have to listen to what I'm saying. Okay. So here it's trivially not allowed. Here it's always allowed. Here's actually where many interesting CFTs live. But the most interesting story from the point of representation theory happens in this rectangle. And you can start looking at it at level 2. So what happens at level 2 is that there is a curve, which I think hits at 1/4. Okay, it doesn't matter where it hits, but it's a curve that looks like it's a kind of a parabola, I think, where everything here is disallowed. So you'll find a negative norm state at level 2. And you can keep going, and you'll find kind of more and more parabolas from higher and higher levels. It's not easy to draw the picture. The parabolas always hit at squares of integers divided by 4. But it turns out that you exclude everything except for a discrete set of points in this region. Mm-hmm. Why C cannot be negative? Yeah, I to be. So for h equals 0, I should know this argument. Sorry, maybe it's maybe you're at level 2. You can see it. I should do the exercise, but so suppose that h equals 0. Suppose h is 0 for simplicity, and then look at the norm of L minus 2, 0C, just as an example. So that's the state L2 L minus 2. Okay, now we can do the commutator because it's a primary, and now Versor algebra tells you that this is proportional to C. Right? There's a contribution from the central term. So C needs to be non-negative for 0H. And I think probably if you go to if you generalize to NH, you can tell me if it works, but I don't remember the answer. I mean, I remember that the final answer looks like that, but I don't know if you need to go to arbitrary level or no. Okay, so what's the picture too? So it turns out in this region, in this rectangle, it's never the case that all of the states have a positive norm, but there's a discrete set of points where the states never have a negative norm, but there are still many states that have a 0 norm. So we need to quotient out by those states, though. So if you want to get a unitary representation, you need to quotient out by the states that have a 0 norm. But you can do that for a discrete set of points, and then you'll find the following. It's a theorem of Friedan, Q. Schenker, and Goddard, canned olive which is that, so what I called RH of Z has no negative norm states if and only if either C is greater than 1 and H is positive, or H is non-negative. Okay, so that's that rectangle up there. Or, okay, now I have to remember the formula. C takes a discrete set of values so here M is any integer starting at 3. 3 for, actually already, or we can already start at 2. And H also takes a discrete set of values. So for a given M, we fix the central charge, and for that M, there is a finite set of values of H where the representation is unitary, which looks like that. So it's M plus 1R minus MS squared minus 1 divided by 4M plus 1. And here R and S are integers satisfying the following inequalities. Okay. Now, okay, maybe, right, okay, so maybe I should explain it a bit better. So, well, okay, let me first make some additional comments. So, furthermore, the representation, which looks like, okay, let me call this CM. So the representation, which is HRS M CM, has null states at levels R times S, and also, where's the O? And also at level M times R and M plus 1R, M plus 1 minus S. I mean, this is not supposed to be obvious. It's a hard, it's a hard theorem, but you can convince yourself that the structure is true by playing with this matrix of inner products at level 2. Maybe you can go to level 3, where it's a 3 by 3 matrix. But okay, this is the statement, and in a unitary theory, we should quotient this representation by all the null states. So the null states are not there; they are truly zero vectors. So let's just look at examples. So the simplest example is m equals 2. So what's C for m equals 2? It's 0. And so R and S, R has to be 1, S has to be equal to 2. And then you get that HRS, so H12, 2 is also 0. If you plug into this formula, m equals 2, R1 S2, then you see here you get 3 minus 2, which is 1, squared minus 1 is 0. Okay, so Friedan, Q, Schenker, Goddard, and Olive tells us that on this line, the only unitary representation is this one. Okay. Then at m equals 3, the central charge is 1/2, which happens to be the central charge of the two-dimensional Ising model. And here we have 3 possibilities for R and S, namely 1, 0, 1, 3, and 2, 3, where the corresponding h can be computed. Here it's 1/16. This one is 1/2, and this one is 0. Okay, so let me delete this drawing, and let me just draw the allowed unitary representations. So here we have c equals 1. Sorry, so c equals 1/2. So Friedan, Q, Schenker, and friends tell us that for c equals 1/2, there are 3 points where you have a unitary representation: 0, 1/6. Okay, let's just say it's 1/16 and 1/2. So I guess 1/2 is about 8 times higher than 1/16. Okay, and these are the only ones that c equals 1/2. And in this way, you can keep going. As m increases, c approaches 1. So there is a sequence of c's getting denser and denser all the way to 1. And at each vertical line, there's a finite number of allowed representations. Yes. If the intersection? Yeah, sorry. So this 1/16. Yeah, good. I'm not sure if it's a maybe sorry, it's not a parabola. That's probably was a mistake. It's a curve which. So the first curve that I was drawing before, coming from level 2, it is a curve which touches 1/4 here, and it passes through these 2 points. Through 1/16 and 1/2. Yeah, I'm not sure if it's a parabola. I don't remember. Maybe it could be a. Yeah, it probably cannot be a parabola because then it wouldn't be in the middle, right? Yes. Yeah. Okay. Then I guess it's not a parabola. It's some algebraic curve of some degree. I don't know what degrees, but it's coming from the level 2, so you can do it. Okay, and all of these curves are such that everything to the left is excluded, and whatever is left at the end of the day is this discrete set of points from r equals m minus 1 and s equal to m. You always get h equals 0, so the identity is always there, and on top of identity, some finite number of them. Well, there is the number of possibilities is m times m minus 1 over 2. So this is the number of distinct h values of h which are allowed. Okay. Okay, but this is not yet conformal field theory. This is just representation theory of a single Loper-Versor algebra. So what is a conformal field theory? Well, firstly, the conformal field theory is a Hilbert space, which is a direct sum of representations. So it's this. And let me also put star. Well, okay, how should I do that? Yeah, let me put star to make sure. So star means that it's the maximally quotiented one, that if there are null states, I remove the null states. Okay, so that's what this star means. Okay, maybe no, star is not a very good. Let's just do a prime. Because star means dual, so let's just do prime. Remove null states. Okay. And in a unitary theory, this H and H tilde have to come from the set of unitary representations, but there are more constraints. I mean, we are not just allowed to take an arbitrary collection of pairs of unitary representations and declare a victory. In particular, there is the crossing equation. So when C is greater than 1, we have the crossing equation as a constraint. So that's that's this one. For any quadruple of representations. But for C between 0 and 1, well, let's say for Cm, we also have the constraints from the null vectors. So so what is a null vector constraint? For example, let's take the example at level 2. So if there's a null vector at level 2, that means that our operator is annihilated by some linear combination of L minus 2 and L minus 1 squared. And this is an identity which imposes additional selection rules on the operator algebra. If you analyze the complete set of constraints, then you'll find that, well, so the set of 3-point functions, we need to ask, what are the allowed 3-point functions? Between which triplet of R and S can there be a non-zero 3-point function? So let me write it like that. This is a problem that can be analyzed separately on the left movers and right movers. So let's imagine we are like the dimensionality of this space of 3-point functions is either 0 or 1, and it's 0 unless R3. Okay, so basically there are some constraints on R3 as a function of R1 and R2. Okay, I think I don't really have time to spell it out, but you can just go to Wikipedia, the page about minimal models, and you'll find that there are some there are some constraints. Okay, unless yeah, well, R1, R2, R3 are constrained, and there are some constraints S1, S2, S3. So if you now, well, we can look at these constraints for the m equals 3 case. Mm-hmm. Mm-hmm. Oh, how can I implement it? Well, so you have your 2x2 matrix of inner products at level 2, and for vectors in this set, for numbers in this set, this matrix is going to have a zero eigenvalue, zero eigenvalue, and the eigenvector is some linear combination of L minus 2 and L minus 1 squared. So the eigenvector corresponding to the zero eigenvalue is this null vector equation. Right, so we saw that for C equal 1/2, we have these three options: 0, 1/16, and 1/2, which I guess they correspond to 2, 3, 1, 2, and 1, 3, R and S. So as an example of these constraints, the 3-point functions are only non-zero for, so when you have 2, 3, which is this, which equals 0, then these two things have to be identical. So it has to be 1, 2, 1, 2. I mean, that's just a statement that the 2-point function is diagonal, so you cannot have, so 2, 3 is identity. So you can have only 1/2, 1, 2, 1, 2, or 1, 3, 1, 3. So this one is kind of obvious. Then when you have 1, 2, 1, 2, so 1, 2, 1, 2 cannot appear in its own OPE. It turns out you can have only identity or the or 1, 3, and so on. Okay, there's a bunch of constraints that. Okay, and in a physical CFT, these selection rules, which are called fusion rules, usually. So the key word here, if you want to read more about it, this is called fusion rules. So fusion rules are something like a holomorphic version of the selection rules on 3-point functions. They need to be satisfied both on the left movers and the right movers. And so in a CFT, they have to be satisfied on left movers and right movers. And furthermore, you also have to satisfy the crossing equation. And finally, what you have to satisfy is modulo invariance that unfortunately we didn't have time to talk about in this course. But it's basically it's consistency on the torus. Consistency of the partition function on the torus. It's kind of it's a generalization of the crossing equation. You can think of the crossing equation as a consistency on the 4-punctured sphere. So this is like consistency on the S2 with 4 mark points. And this is a consistency on T2. So putting all these constraints together, there is a complete classification of unitary 2-dimensional CFTs. Whose central charge is between 0 and 1. These 2D CFTs are called minimal models. here. So there are, well, there are essentially three infinite, well, there are two infinite classes and one finite, and three extra ones. So it's a kind of ADE type classification. I won't talk much about these, but these are the most famous ones. So these are the A-type minimal models, where the only combinations of left and right movers which appear are identical. So let's focus on the for the A-type, it's labeled by the same M as before. Which can be, from 2, 3, 4, and so on, where the Hilbert space on S1 contains precisely one of each of the diagonal allowed combinations of R and S. So it's a direct sum where R goes from 1 to M minus 1. S goes from R plus 1 to M. And we have the representation of two copies of Virasoro algebra from which we have removed all of the null vectors. And on the left, we have the same H as on the right. And the central charge is the central charge Cm. Okay. And in this theory, all of the 3-point functions are fixed. So we can talk about like 3-point functions of R1 S1, R2 S2. It's fixed from the crossing equation. And several very important two-dimensional CFTs are in this class. Yes. Yes. I can. Well, I think we are running a bit low time, so I'm being a bit telegraphic. But essentially, crossing symmetry in this case becomes a finite-dimensional problem because there are only finitely many conformal primaries. So you can, instead of the huge infinite-dimensional problem that we discussed in the previous lectures, now it's a finite-dimensional vector problem, and you basically get finitely many linear equations for finitely many unknowns, so you can solve it. And well, originally it was Belavin, Polyakov, and Zamolodchikov who solved it for the two-dimensional Ising model. So what are these theories? So for m equals 2, it's the trivial fixed point. So quite boring. For m equals 3, we have central charge 1/2, and the Virasoro primaries, there are 3 Virasoro primaries of conformal dimensions. So now I will write H tilde. It's 0, 0, 1 over 16, 1 over 16, and 1/2, 1/2. And this theory is also known as the two-dimensional Ising model. Where this one has the interpretation of the sigma field and this one has the interpretation of the energy field. So this one corresponds to changing the temperature, and this one corresponds to turning on the magnetic field. And the selection rules, the fusion rules, which I was writing about before, amount to the statements that, so this is the identity. When you take the OP of identity with sigma, you have sigma. OP of identity with epsilon, you get epsilon. Sigma, sigma gives you 1 plus epsilon. Sigma, epsilon gives you just sigma. And epsilon, epsilon only gives you identity. So you can interpret these either as on one holomorphic side, in which case there are some statements about fusion rules of a representation of a single Virasoro, or you can interpret it as a statement about these diagonal fields that have the same left and right moving conformal dimension. So this is just a schematic way of saying, if we implement all of the null vector equations, what are the kinematically allowed 3-point functions? So it has nothing to do with CIJKs. So CIJKs are the actual coefficients sitting in front, which talk about the holomorphic times anti-holomorphic objects. These are just the statements about what is kinematically allowed from implying all the null vector equations. So without any null vector equations, anything is allowed, like any three Virasoro. So for C greater than 1, any three H1, H2, H3 have a allowed 3-point function. For C between 0 and 1, this is no longer the case. There are extra selection rules coming from null vectors. Okay, so well, this is how you can solve some 2D CFTs. What else do I want to say? So this gives you an infinite set of 2D CFTs labeled by increasing m. For the two-dimensional Ising model, you can do much more than just these 3-point functions and OP coefficients. You can actually determine all of the endpoint functions of any of these Virasoro primary fields. Then you can ask, now we can kind of start thinking about the space of all QFTs, because we have this great handle on a nice subset of fixed points without ever mentioning any Lagrangian. And we start these lectures by talking about RG flows in some space of QFTs in which there are various CFTs living as fixed points, and QFTs can be thought of as flows between different CFTs. So we can start asking about flows between these minimal models. So these A-type minimal models, for example. So to understand the flows, the first point is to list the possible operators and